All right, welcome back to linear algebra. In this first of two lectures in section 6.4, we're going to introduce something called a normal operator. Our motivation for this section is kind of trying to answer the question, under what circumstances does a linear operator on a finite dimensional inner product space have an orthonormal basis that consists entirely of eigenvectors? All right, so when can we diagonalize a linear operator on a finite dimensional inner product space using an orthonormal basis of eigenvectors? Okay, so to get going here, our first main result, called shears theorem, I want to prove a little lemma. So if we take a linear operator on a finite dimensional inner product space V, the lemma is that if that operator has an eigenvector, then so does its adjoint. Okay, so to give the proof of it, let's suppose that I've got some non-zero vector V, and it's an eigenvector for my linear operator on this finite dimensional inner product space. Let's call its eigenvalue lambda. Okay, so now if we take any x in this inner product space V, certainly the inner product of 0 with x is going to be 0. But if V is an eigenvalue with eigenvalue lambda, then the operator T minus lambda times the identity applied to V will be 0. So I'm just making a substitution there. And then I'm going to move that operator T minus lambda IV across the comma, quote unquote. So I'm looking at its adjoint applied to X. And by properties of adjoints, the adjoint of T minus lambda times I is the adjoint of T minus lambda bar times the identity. All right. So what does that show? That shows that for every x, T star of lambda bar times 1 of x is orthogonal to the vector v. Okay, so that shows that v, this non-zero vector, it's in the perpendicular space to the range of that operator T star minus lambda bar times 1. Because this x ranges over all vectors in V, this thing that I'm underlining will range over the range. V is orthogonal to everything in that range. That's what it means to be in the perp space. All right. So that means that in particular that the range is not all of V, because if its perpendicular space is not 0, it can't be the entire vector space. The only subspace whose perpendicular space is 0 is the entire vector space. Right? So if that range isn't everything, well, the dimension theorem, reaching way back into our theory, it implies that the null space can't be 0, because the dimension of the null space plus the dimension of the range has to add up to the dimension of V. So the dimension of the null space has to be at least 1. And if that null space of T star minus lambda bar isn't 0, it means it has a non-zero vector in it. So it means that lambda bar is an eigenvalue for T star. Okay, so that proves the lemma. Before we state the main theorem here, Schur's theorem, I'm going to introduce a definition. I'm going to call a subspace T invariant. T is a linear operator on V if the image of anything in the subspace, again, belongs to the subspace. Okay, so another way to say that is if you take the restriction, and the author denotes the restriction by T sub W, so the restriction, I just mean limit the domain to only vectors in W. If W is T invariant, then that restriction is itself a linear map from W to W. The restriction's domain to W, of course, is W, and if it's T invariant, then the codomain is also W. So if you like, a T invariant subspace is one in which the restriction to it is also a linear operator on it. Just as a real quick example, if you take, say, an eigenspace for an eigenvalue called lambda, that eigenspace is T invariant. Well, because T of V is lambda times V, which is any scalar multiple of an element of a subspace is again in that subspace. So eigenspaces are T invariant subspaces. Okay, so here's the main theorem, Schur's theorem, theorem 6.14. So what does it say? It says we have a linear operator on a finite dimensional inner product space called T, and we're going to suppose that the characteristic polynomial splits. That is, that the characteristic polynomial for T factors completely into linear factors over our scalar field F. Okay, and then what is the conclusion? That there's an orthonormal basis beta for V such that the matrix is upper triangular. The matrix for T is upper triangular. So the shears lemma is that if you have an operator on a finite dimensional inner product space whose characteristic polynomial splits, then you can write the matrix of that operator as an upper triangular matrix in some orthonormal basis. So we're going to prove that by induction on the dimension of V. If the dimension of V is 1, there's sort of nothing to do. You can take any non-zero vector in B and take your orthonormal basis just to be the unit vector in that direction. The matrix of T in that basis is just 1 by 1. Every 1 by 1 matrix is upper triangular. So there's nothing to do in the case that the dimension of V is 1. So let's suppose our induction hypothesis that this theorem holds for all inner product spaces of dimension n for some n greater than or equal to 1. And then let's take an inner product space that has dimension n plus 1, take a linear operator on it, and suppose the characteristic polynomial of splits. Okay, so I want to show that that operator, that there's a basis for which its matrix is upper triangular. Okay, so if the characteristic polynomial splits, the operator has to have an eigenvector, right? Because it splits, so we have eigenvalues, and every eigenvalue has an eigenvector. And using the lemma that we just proved, the adjoint also has an eigenvector. If T has an eigenvector, so does T star. So let me call the eigenvector Z. So Z is some non-zero vector, and T star of Z is lambda Z for some scalar multiple lambda. All right, the subspace W, take it to be the line through Z, all the scalar multiples of this non-zero vector. Okay, so I claim that the perpendicular space to that line, which is dimension, remember the dimension of W, maybe I'll just write it here. The dimension of W is 1, scalar multiples of a fixed non-zero vector. So the dimension of W perp is going to be the dimension of the space minus 1, that is, it's going to be dimension n. And I claim it's T invariant. So the restriction of T to W perp is also a linear operator. So to show that, I have to show that if you take T of something in W perp, it's again in W perp. So let's let X be in W perp, take a vector in it, and I want to show T of X is in W perp. Maybe I can write that here parenthetically. I want to show T of X belongs to W perp. So that's why I'm starting off by saying, well, let's take the inner product of T of X with the basis vector of W. W is one-dimensional. And then using the usual computation, if I use the adjoint property, I can move that star over. We said that T star of Z is lambda times Z. Lambda comes out with a conjugate from the second coordinate, but X is in W perp, Z is in W, so the inner product of X and Z is 0, and lambda bar times 0 is 0. All right. So if you take any element of W, any scalar multiple of Z, the inner product of T of X with that scalar multiple is 0 by the above computation. So T of X is in W perp. That establishes our claim. Okay, so we've shown that W perp is T invariant. We didn't delve into the material and determinants, and I also kind of skipped over a big theorem in linear algebra, the Cayley-Hamilton theorem. So I'm going to just sort of quote something here. An unproved theorem 5.21 says that because W perp is T invariant, the characteristic polynomial of our operator restricted to W perp is a factor of the characteristic polynomial for T. Okay, the characteristic polynomial for T splits. This thing factors completely into linear factors over F. So do both of these things because their product equals each other. Since F of T splits, so does the characteristic polynomial of the restriction to T to W perp. Okay, so we already remarked above that W perp has dimension n because it has to add 1 plus it has to be n plus 1. So by the induction hypothesis applied to the operator T restricted to W perp has some orthonormal basis, call it gamma, its elements V1 to Vn, such that that restriction in that basis is upper triangular. All right. So let's extend that to a basis for all of V by just taking the gamma basis vectors and adding in, well, not Z, because it might not have length 1, but divide it by its length. So that's a unit vector. You know that Z is perpendicular to all these V's because, well, the V's come from W perp and Z is in W. So it takes a little bit of thought, but beta here is an orthonormal basis for V. And if we think about what the matrix of T in that beta basis is, well, when you take T of the first basis vector, T of Z over Z bar, Z was an eigenvector for T star with eigenvalue lambda. So our work in the lemma shows that that Z is an eigenvector for T with eigenvector lambda bar. So you're going to get lambda bar plus none of the other V's. And then W perp is T invariant. So when you take T of any of these guys, you get elements of W perp. Yeah, this lower right-hand corner is an upper triangular matrix. So this whole thing, its only non-zero entries could be in the upper triangle. Okay, so that shows by induction this shows that T has such a basis. And then since V was any inner product space of dimension n+1, by induction, the theorem holds for all n. Nice. Back to our goal. Suppose that we have this orthonormal basis of eigenvectors for T. Well, then in that basis, the matrix for T is diagonal. Yeah. But the matrix for T star is the adjoint matrix for T. So the transpose conjugate, that's also diagonal. The transpose conjugate of a diagonal matrix is diagonal. Diagonal matrices commute. When you multiply two diagonal matrices, it doesn't matter what order you multiply them in. Yeah, but the matrix of operators and bases we've proved is the matrix of the compositions. And if those two matrices are equal, then the operators are equal. So to summarize, if there's an orthonormal basis of eigenvectors for T, T has this property that when you compose it with its adjoint, you get the composition in the other order. TT star is T star T. So we're going to give a name for such operators. We're going to call T, this is kind of one of the most abused terms of all of mathematics, but we're going to call T normal if T times T composed with T star is T star composed with T. For matrices, we'll call them normal if the product of their adjoints is, if it commutes with its adjoint. Okay. So if you have an orthonormal basis and you take some operator, it's going to be normal if and only if its matrix is normal, because remember, the matrix of T star is the star of the matrix of T. So an operator being normal and a matrix in an orthonormal basis being normal, they're equivalent notions. All right, so we're going to end this video lecture by looking at some properties of normal vectors. We're going to kind of achieve our main goal in the next one. So for this time, we just have to get used to properties of normal vectors, or operators, excuse me. So suppose we have an inner product space, finite dimensional. It's actually okay if it's not, but for our purposes, we'll assume it's finite dimensional. And suppose we have some normal operator on it. So we have some operator. Let me just remind you, because the definition is brand new, that its composition with its adjoint is the same composing in either order. So this theorem has four parts. One says that T and T star have the same length for every vector. Okay, so the length of T of X and the length of T star of X is the same. The second part is that T minus any scalar multiple of the identity is also normal. It also satisfies such an equation. The third part, which we've kind of already proved, that if you have an eigenvector for T, then you also have one for T star. And in fact, the eigenvalue just gets conjugated. And then fourth and finally, if you take two distinct eigenvalues of T, and you call, say, two of their eigenvectors, respectively, x1 and x2, that those things are orthogonal. Right? We've proved in the past that that eigenvectors from distinct eigenvalues are linearly independent. This is saying something even stronger, that they're going to be perpendicular to each other. T is a normal operator. Okay, I'll keep scrolling back here, but I just wrote out the proofs of these things one at a time. So let's check them out. So for A, I want to show the lengths are the same. So take a vector, and as usual, I'll think about the length squared. Why? Because I can express that in terms of the inner product and then using the adjoint property. But T star T is TT star, okay? And then I move the T back across the comma, putting a star on it, and that's the length of T star of X squared. Take square roots of both sides and you proved A. So that's the proof of A. For the proof of B, I want to show T minus C times I is normal for every C. Okay, so pick a C. Pick a C in the field, and let's look at that operator times its adjoint, composed with its adjoint. Okay, by properties of adjoint, T minus Ci star is T star minus C bar I star, but I star is I. And then just distribute out, so quote unquote FOIL. Okay, here I'm using the normality of T, the T star is T star T. The rest I'm just rearranging terms. The minus C bar times T I put here, minus C times T star I put there. C bar commutes with C, and then just kind of refactor it. Use the property of adjoints one more time, and there you go. I've shown that this operator composed with its adjoint is its adjoint composed with it. That's what normal means. Kind of doing some super scrolling here. Hopefully you're not getting seasick, but that proves B. To prove C, I want to show that if you take an eigenvector for T, it's also an eigenvector of T star with the conjugate eigenvalue. So let's look at, say, for any x. So for an x in V and a lambda in F, let me look at the length of Tx minus lambda x. Yeah, I'm going to look at the length of Tx minus lambda x. I just rewrite that operator in that form. And now we just proved that for normal operators, the length of their image at x is the same for the adjoint. So by part A, applying part A to the operator T minus lambda I get that. Push the star through. So you get T star minus lambda bar times x. And those things are the same. So therefore, this side is equal to 0 if and only if that side is equal to 0. Said another way, T of x is lambda x if and only if T star of x is lambda bar of x. That's what part C says. And then for part D, instead of scrolling back, I'll just remind you that x1 is an eigenvector with eigenvalue lambda 1, x2 is an eigenvector with eigenvalue lambda 2. And let's look at this computation. Let's look at lambda. I want to show x1 and x2 are orthogonal. So let's look at lambda 1 times their inner product. Push lambda 1 in, okay? But lambda 1 times x1 is T of x1, and then move the T over, putting the adjoint on it. But T star of x2, we just proved x2 is also an eigenvector for T star with eigenvalue lambda 2 bar. So T star of x2 is lambda 2 bar times x2, and then bring lambda 2 out of the second coordinate, the conjugate goes away. So what does that show? If I subtract, say, the right-hand side of that from the left-hand side, it shows that lambda 1 minus lambda 2 times that inner product is 0. But we were supposing that lambda 1 and lambda 2 were distinct eigenvalues, so it must be that the inner product is 0. That is, x1 is orthogonal to x2. Okay, so just to kind of summarize here, what we've shown so far in this lecture is that if T has an orthonormal basis of eigenvectors, then it's normal that T star is equal to T star T. So we'll pick this up next time in the next video lecture, but it's a nice surprise that for inner product spaces over the complex numbers, the converse of that is true. That if T is normal, then it has to have an orthonormal basis of eigenvectors. So that's going to be kind of our answer to our question. When does an operator over a complex inner product space have an orthonormal basis of eigenvectors? Well, it's if and only if it's normal. Over real vector spaces, the answer is a little bit more complicated, but over complex vector spaces, this necessary condition is going to turn out to be sufficient. Okay, so that's where we'll stop it for here, and thanks for listening.